All right, today we're tackling one of the most powerful and maybe one of the most overlooked tools for training machine learning models, learning rate scheduling. Seriously, this concept can be the secret ingredient that takes a model from just okay to absolutely state of the art. To really get this, I want you to imagine something. Picture yourself as an explorer, standing in a huge, foggy mountain range. Your one and only job is to find the absolute lowest point, the deepest valley around. The catch? You can only see a few feet in front of you. So the big question is, how big of a step should you take? Think about it. If your steps are way too big, you could literally leap right over the valley you're looking for without ever knowing it was there. But, on the other hand, if your steps are too small, you might wander into a tiny ditch and think you found the Grand Canyon. Or, just take forever to get anywhere meaningful. This right here is the problem with a fixed step size.
And that brings us perfectly to what we call the learning rate dilemma. Because that step size our model takes as it learns, well, that's what we call the learning rate.
Now for the more formal definition. The learning rate is the hyperparameter that dictates how much our model's internal brain, its weights, get adjusted every time it gets something wrong. It's basically the throttle on our model's learning engine. And as you can imagine, picking one perfect speed at the very beginning of a long journey, well, it's pretty much impossible. So, what's the solution? What if our explorer had a map that wasn't static, but dynamic? One that updated itself based on the terrain they were crossing? Well, that's exactly what learning rate scheduling is. It's a smart, strategic plan for changing our step size as the journey progresses. And why is this such a big deal? Well, a good map helps our explorer find that valley way faster. It keeps them from getting trapped in those misleading little ditches, what we call local minima, and ultimately it just leads to a much more successful mission. For our models, this means they train faster, perform better on new data, and the whole training process is just a lot more stable and reliable. Okay, so we've established that our explorer needs a map. Let's take a look at some of the most popular maps, the different scheduling strategies they can use to navigate this complex landscape. First up is the old classic, step decay. This is probably the simplest strategy you can imagine. It's like our explorer decides that every mile they travel, they're going to shorten their stride. You start with a certain step size, and after a specific number of training cycles, you just cut it. Simple as that. Now, the beauty of step decay is that it's super easy to implement, and honestly, it works surprisingly well for a lot of common models. But, and this is a big but, those sudden abrupt drops in the learning rate can sometimes shock the model a little bit, destabilizing the training. Plus, you have to manually decide when to drop the rate and by how much, which feels a lot more like guesswork than science sometimes. So if you're looking for a less bumpy ride, there's exponential decay. Instead of those sudden drops, this schedule makes the learning rate smaller, smoothly, and continuously. Think of it like our explorer's stride, getting just a tiny, tiny bit shorter with every single step they take. It's a much more gradual process. The big win here is stability. That smooth descent avoids the jarring shifts you get with step decay. The catch, though, is that you have to choose that decay rate really carefully. If you're too aggressive, your learning rate could practically disappear before the model has had a chance to learn much. But if you're too gentle, you're barely making a dent at all. Okay, this is where things get really interesting. So far, every strategy we've talked about is based on one idea: start big, end small. But does the learning rate always have to go down? What if that's not the best approach? This one question completely changes the game and opens the door to some really clever modern strategies. And that question leads us to a much more elegant approach, cosine annealing. Imagine the learning rate follows the gentle, swooping curve of a cosine wave. It starts high and decreases slowly. Then it speeds up its descent right in the middle of training, and then crucially, it slows down again for a really soft landing as it hones in on that final solution. This smooth, nonlinear path often leads to much better results. But here's an even cooler trick you can do with it: warm restarts. That's where you periodically reset the learning rate back to a high value. It's like giving our explorer a temporary jetpack to blast out of a valley they might be stuck in so they can get a better look around and maybe find a deeper, better valley somewhere else. All right, now for a strategy that's even bolder: cyclical learning rates, or CLR. With this one, we throw out the only go down rule completely. Instead, we intentionally make the learning rate bounce up and down between a minimum and maximum value. Our explorers now, on purpose, taking giant leaps again from time to time, hoping to jump clear of any suboptimal areas and get a much better view of the entire landscape. This is based on a really powerful insight. Sometimes, to find the true best solution, you have to be willing to explore more broadly, even if it feels like you're going backwards for a bit. By periodically cranking the learning rate back up, CLR encourages the model to escape those local minima. And it often means you don't have to stress so much about finding that one perfect starting rate. And if we take this whole idea to its logical extreme, we get what's known as the OneCycle Policy. This is a really popular, state-of-the-art approach that does exactly what it says: one big cycle. You start with a very low learning rate, then you warm up to a maximum value about halfway through training, and then you cool down all the way back down and even lower for the rest of it. It's a very disciplined journey, and it has produced some absolutely incredible results. Now, a quick but really important aside. Some of you are probably thinking, hey, what about optimizers like Atom or RMS Prop? Don't they already handle this? And you're right, they do, to an extent. You can think of these as explorers with smart shoes that automatically adjust their stride for different kinds of terrain. They have their own built-in logic. But, and this is key, they often benefit even more when you pair them with a big picture map, a global schedule like the ones we've just talked about. Okay, that was a whirlwind tour of the maps, but now for the million-dollar question. Which one should you actually use for your project? Let's get practical. So while there's no single magic answer, there are some really good rules of thumb. If you're working with something like a convolutional neural network for images, step decay and cosine annealing are fantastic places to start. For those giant, complex language models like transformers, a warm-up period is pretty much non-negotiable. And of course, the size of your data set and how long you have to train are going to play a huge role in your decision too. And here are a few pro tips to keep in your back pocket. First, use a tool called a learning rate finder to get a good sense of the best starting rate before you even begin. Second, always watch your training and validation loss. The numbers will tell you if your map is working. And hey, don't feel like you need to get super complicated right away. Sometimes simple step decay is all you need. The best part is all the major frameworks like PyTorch and TensorFlow have these schedulers built right in, so it's really easy to experiment. So let's just zoom all the way back out. What we've been talking about isn't just about tweaking a tiny number. Learning rate scheduling is a fundamental, strategic tool for unlocking the absolute best performance from your deep learning models. And look, don't just take it from me. This quote from the source material really hits the nail on the head. The people building groundbreaking models like GPT and ResNet, they don't just pick a learning rate and cross their fingers. No way. They use carefully designed, intelligent schedules. Mastering this is a non-negotiable skill that really separates the amateurs from the pros. So, I'll leave you with this thought. Every single time you hit train on a model, you are sending an explorer out on a critical journey. And whether you realize it or not, you're giving it a map. The only question is, are you giving it the right one? Thanks for joining us for this explainer.